Hello, game theorists. So let's go over the attack and defense game. Only a couple of the groups found the Nash equilibrium strategy. So let's talk about how to set the problem up and how to solve it. So you guys probably figure out there are no dominated strategies, so you can't eliminate anything. So your randomization will probably involve all three strategies. Let's say our attacker is going to play air with probability PA. They'll play land with probability PL. That means they'll play C with probability 1 minus PA minus PL. It's going to be similar for a defender. Defender plays air with probability RA. Defender plays land with probability RL. And C with probability 1 minus RA minus RL. So the first thing I have to do here is set up the expected payoffs. I'll just start with the attacker. So if we're here, attacker gets 0. That occurs a probability PA times RA. That's because the attacker plays air with probability PA and defender plays air with probability RA. So PA times RA is the probability that we're over here. If we're here, the attacker gets 10. That occurs a probability PA times RL. If we're here, attacker gets 5. That occurs a probability PA times 1 minus RA minus RL. We're over here getting 3 with probability PL times RA. This just gives us 0. So 0 times PL times RL. I get 2 with probability PL times 1 minus RA minus RL. Last row. So we're here and getting 4 with probability 1 minus PA minus PL times RA. We get 1 with probability 1 minus PA minus PL times minus PA minus PL times RL. And we're here with, well, we get 0, so it doesn't matter. The 0 is just going to cancel out all those probabilities. While we're on the topic of canceling out, these guys go away. So we've got our attacker's expected payoff. So to maximize that payoff, the attacker is going to take partial derivatives with respect to PA and PL. That's because the variables they control are PA and PL. You're picking those two probabilities if you're an attacker. So we take those partial derivatives and set them equal to 0. So by the way, so see how the game is set up. If the defender anticipates what you're doing, if they know you're playing air and they play air, then they effectively block you and you get 0. But if you're the attacker and you can surprise the defender, like if you play air but they're expecting land, then you get a positive payoff. That's the idea. All right, so let's go take our partial derivatives. So for this first term, the partial derivative with respect to PA is 10 times RL. For the second term, partial derivative with respect to PA is 5 times 1 minus RA minus RL. There are no PAs in this third term, so that one just goes away. No PAs here either, so that one also is going to just go away. We do have a PA over here. So that PA is multiplied by a minus sign, a 4, and an RA. So that comes out to minus 4 RA. So originally we have minus 4 PA RA, but when you take that derivative with respect to PA, you just get minus 4 RA. All right, we have another PA over here. It's being multiplied by a 1. We got a minus sign, and we have an RL. So that's going to come out to, you take the partial derivative, minus RL. So just expand that, you get minus PA RL, but the partial derivative of that with respect to PA is going to be minus RL. So that's our partial derivative with respect to PA. We set that equal to 0. Next step, let's take our partial derivative with respect to PL. So there's no PL over here, so that one just goes away. No PL over here either, so that one also goes away. Here we've got a PL. That's multiplied by 3 in RA, so that partial derivative is going to be 3 times RA. We have another PL over here, so that partial derivative is going to be 2 times 1 minus RA minus RL. We have a PL over here. It's being multiplied by 4 RA, and we have a minus sign. So that'll be minus 4 RA once we take partial derivatives. We have another PL over here. It's got a 1, a minus sign, and RL, so that'll be minus RL once you take partial derivatives. All right, so we got the attacker's partial derivatives, and we set them equal to 0. So we just got to solve those two equations for these two unknowns, RA and RL. So I guess the first thing to do would be to expand these terms in parentheses. So we get 10 RL plus 5 minus 5 RA minus 5 RL. So the 5 minus 5 RA and minus 5 RL. We get that. I'll do the same thing down here. I have 3 RA, and this will be plus 2 minus 2 RA minus 2 RL minus 4 RA minus RL equals 0. Let's start combining like terms. I have some RAs over here, and I have some RLs. So this top equation becomes 10RL minus RL minus 5RL. So 10 minus 5 minus 1 is going to be 4RL. Then you have minus 9 RA, because minus 5 minus 4 is minus 9. We have a plus 5. That equals 0. So that's our top equation simplified. Now let's go work with the bottom one. 3RA minus 2RA minus 4RA, that's going to be minus 3RA. Minus 2RL minus RL is minus 3RL. Then we have just a plus 2 over here. And all that equals 0. So that's made things a bit easier. Let's see, what do I want to do next? Let's move this 3RA to the other side. So I get 3RA equals minus 3RL plus 2. So I just added 3RA to both sides, and I kept this as is. If you divide both sides by 3, you get RA equals minus RL plus 2/3. So that can be substituted up over here. So what does that give us? So I have my 4RL minus 9 times RA, but I know RA is this. So 4RL minus 9RA plus 5 equals 0. Let's expand. So minus 9 times minus RL is plus 9RL. Minus 9 times 2/3 is going to be minus 6. So I combine these guys and I get 13RL. Combine those guys, I get a minus 1. So 13RL equals 1, which means RL is 1 over 13. I can plug that in over here to find RA. So RA is minus RL plus 2/3. RL is 1/13. So let's get a common denominator. So to do that, I'll multiply it 1/13 times 3 over 3. So multiply by 1, so I'm not changing the value here. I'll multiply it 2/3 by 13 over 13. Again, multiply by 1, you don't change the value. What does that give us? We get minus 3 over 39 plus 26 over 39. So 26 minus 3 is going to be 23. And that is RA. All right, so we found RA and RL. We got that by looking at the attacker's expected payoff. We took a partial derivative instead equal to 0. Now we have to do the same thing for a defender. Find a defender's expected payoff, take partial derivatives, set them equal to 0. So let's do that. So pi d is defender's payoff. So defenders are a column player. Column players' payoffs always come second. We could be over here getting 0. Probably that happening is PA times RA. We could also be over here getting minus 10 for a defender. That probability is PA times RL. So PA, RL. We could also be over here getting minus 5. That gives the probability PA times 1 minus RA minus RL. We could be here getting minus 3. So you're probably PL times RA. We could also be here getting 0. 0 times PL times RL. We could get minus 2. Probably PL times 1 minus RA minus RL. Could get minus 4. 1 minus PA minus PL times RA. We could get minus 1. So 1 minus PA minus PL times RL. We could also get 0 over here, but the 0 is going to cancel everything out, so I won't worry about that one. And we can get rid of these guys. So now I've got the defender's expected payoffs. The two variables the defender controls are RA, the probability the defender plays air, and RL, probability they play land. The probability they play C is pinned down by those other two because all probabilities must sum to 1. So what we're going to do here is take partial derivatives with respect to RA and then with respect to RL and set those equal to 0. So there's no RA over here, so this term would just go away. We do have an RA over there. It's multiplied by minus 5PA and a minus sign. 2 negatives make a positive, so that'll be a plus 5PA. Here we've got RA times minus 3PL, so that partial derivative is just minus 3PL. Our RA over here is multiplied by a minus sign and a minus 2PL. So once again, 2 minus and we have plus. So we have plus 2PL for that partial derivative. Here RA is multiplied by all that stuff, so let's keep that. Minus 4 times 1 minus PA minus PL. No RA's over here, so that one goes away. And that's our first partial derivative. All right, our last derivative. Now I take with respect to RL. So we have minus 10 PA times RL. So minus 10 PA. We have an RL over here times a minus 5 PA and a minus sign. Two negatives make a positive, so plus 5 PA. No RLs over here, so this one goes away. That one's got a 0 in front of it, so that one goes away too. Here's our next RL. So minus 2 PL and a minus sign. As always, two negatives make it positive, so plus 2 PL. No RLs over here, so this one goes away. We have an RL over here, though, so that one stays. And we get minus 1 minus PA minus PL. And all that equals 0. So we're done with our calculus. Now it's just a matter of algebra. So I start down here. PAs I'll combine. Minus 10 PA plus 5 PA. And I have that over here. And I have some PLs as well. So minus 10 plus 5. But I have a plus 1 over here. Remember, 2 minus to make a plus. Let me just write that out just to make it clear. So minus 10 PA plus 5 PA plus 2 PL minus 1 plus PA, minus times minus is plus PL equals 0. So minus 10 PA plus 5 PA plus PA is minus 4 PA. Plus 2 PL plus PL is going to be plus 3 PL. I still have that minus 1 over there. So that's our bottom equation. Let's equals 0. Let's expand our top equation here. 5 PA minus 3 PL plus 2 PL. Minus 4 times 1 is minus 4. Minus 4 times minus PA is plus 4 PA. Minus 4 times minus PL is plus 4 PL. And all that equals 0. Combine PAs. Combine PLs. So that top equation rewritten, 5 PA and 4 PA is 9 PA. Minus 3 PL plus 2 PL plus 4 PL will be plus 3 PL. And I've got a minus 4. And that equals 0. How do I want to handle this one? I've got a 3 PL in both of these, so it'd be handy if I could sub that out. So over here, 3 PL, if I push these guys to the other side, is 1 plus 4 PA. Same thing over here, 3 PL. I'll push these two to the other side. That'll be 4 minus 9 PA. So if you sub those out, here's what happens. One plus 4 PA is 4 minus 9 PA. So I'm going to get 13 PA equals 3. So PA is 3 over 13. we can sub that in over here. 3PL is 1 plus 4 times PA, but PA we just established was 3 over 13. So that'll be 1 plus 12 over 13 is 3PA. Sorry, 3PL. So 3PL is, just to get a common denominator, so 1 is 13 over 13. I still have 12 over 13. 3PL is 25 over 13. Divide both sides by 3, and you get that PL is 25 over 39. So that's how you find the randomization the players use in the Nash equilibrium. So you can probably see that was a lot of math. It was still tractable for a 3x3 game, but what if you somehow got like a 4x4 game or a 5x5 game or something even more complex than that? Then you could be doing algebra all week. So for really big problems, it helps to have a computer to help you work through them. Now, instead of just saying use a computer, I'll actually show you a program you can run in order to do these calculations. So be sure to come back for our next episode and see how to use a computer to work with some of these problems.